So welcome student friends for these lectures on digital techniques. So in the last lecture we had discussed about half adder, which has two inputs and two outputs. We had discussed the types of adders, binary adder circuit, which are half adder and full adder. So in the last lecture we had discussed about half. Now this half adder has one disadvantage, drawback or limitation. So the limitation is half adder cannot perform addition of 3 bits because it can only perform addition of 2 bits, right? And in the case of this addition, like if you consider example here, if you consider example, if I have 128 and 287, if I have this addition, so here you can see 3 bits addition are needed. So in this case we cannot use half adder because half adder will only consider these 2 inputs. And what about this? Or even if you take this 28 and 87, so if we even take here this 8 plus 7 is 15 and carry 1, right? Now here this becomes 2 bits, but now 8 plus 2 is 10 plus 1 11. So what about this carry? So half adder, in half adder this carry is neglected, or it cannot take this carry because it has only 2 inputs. So as to avoid this drawback or overcome this limitation, we use full adder. So the addition of 3 bits is not at all possible by using half adder circuit. That's what I have explained here. Therefore cannot be used practically. So half adder is not used practically, right? Hence we go for so it cannot be used practically. Therefore we go for this full adder circuit, which is again a combinational logic circuit which has 3 inputs and 2 outputs. Now this overcomes the drawback of half adder, right? So you can see here it has this is a block diagram of full adder. It has 3 inputs A, B and C in, which is carry in. This C in means carry in. The third bit here, this one or this one, and it has two outputs. This is sum and this is carry out, the output carry, right? Now since this is 3 inputs, we have 3 inputs, so 2 raised to 3 is 8. We have seen for 3 inputs we have 8 different combinations, and that combinations are 0, 1, 2, 3, 4, 5, 6, 7. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Now let's see the output of these 3 combinations. So 0 plus 0 is 0, 0 plus 0 is sum is 0, carry is also 0. 0 plus 0, sum is 0, right? 0 plus 1, sum is 1, carry is 1. This is again 0, 1. Now 0 plus 1, sum is 1, 1 plus 1, sum is 0, carry is 1. So if you have 2 ones, then sum is 0, carry is 1. So again this is 1 plus 0 is 1, 1 plus 0 is sum is 1, carry is 0. 1 plus 0 is 1, sum is 1, right? And 1 plus 1, sum is 0, carry is 1. So here also 0, 1. Now here this is a triple 1. So you have to always remember triple 1, sum is 1, carry is also 1. We have already discussed this in our binary arithmetic, right? So this is the output column for sum and output for column for carry out. Okay, right? So this is output for sum and this is output for carry. Now we are supposed to design the circuit for this sum and carry, right? So in the last lecture we have seen, first we need to have truth table. From the truth table we can go for K map, and from K map we can find logical expression, and from this logical expression we can design the circuit. Okay, so without having this expression you cannot design the circuit. And from where do we get this expression is from K map, right? And K map we get from truth table. So that is what the steps we have followed. Now let's try for this sum. So I can say K map for sum, since it is 3 input variable K map. Okay, so I'll draw here. Let's K map for sum S. So here we have taken A, B, this is C, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Okay, this is C bar C, A bar B bar, A bar B, A B and A B bar. Okay, so this is the K map for the sum output. Now let's fill this. So 0, 1, 2, 0, 1, 2, 3, 4, 5, 6, 7. Right? So I have just mapped this column with the K map. Okay, and how many groups are formed here? Now here if you see, all the ones are individual here. There is no one present in respective adjacent cells. कोई भी 1 के बाजू में adjacent cells के में 1 नहीं है, तो ये individual groups हो जाएंगे. 1, 2, 3, 4. So 4 groups are formed here. So let's say group 1, group 2, group 3 and group 4. Okay. So we can directly pick that value. So I can write S equal to what is group 1? A bar, B bar, C. This we can consider C in. Okay, so this is A bar, B bar, C in plus what is group 2? A bar, B, C in bar. You can see if we go this way and this way, plus this group 3 is A, B, C in, and group 4 is A, B bar, C in bar. Okay, so if you take here, you can see, you can take this C in common and C in bar common here, right? So this equation turns out to be C in A bar B bar plus AB plus C in bar A bar B plus A B bar. Okay. Now this equation has a very much lengthy derivation. So here I would skip that derivation and would come to the concluding part. So sum is A, B, C in, right, which is represented as 3 input XOR gate. 3 input XOR gate. Okay, so if you are interested to know about this derivation, you can just try yourself, or I can post you this derivation on your personal WhatsApp, right? But for now, just understand that the final this equation for full adder sum is sum equal to A, B, C in, right, which is simply 3 input XOR gate. Okay, so this is for sum. Now let's see for carry. So as I said, if you want to design a circuit, you need to design K-map for each output column of a truth table. Okay, so we will require this output. Now if you go for this K-map for carry or carry out, that is C out. Okay, so again it's 3 input variable. So this is A, B, C 0 1 0 0 0 1 1 1 1 0. This is C bar C. This is A bar B bar, A bar B, A B and A B bar. Okay, now here what are the entries? So 0 0 0 1 0 1 2 3 4 5 6 7, right? So if you look at the C out column in the truth table, this is how it is mapped with K map. Now how many groups are formed here? A quad, no, not quad, but pairs are formed here. And how the pairs are? This is 1, this is 2 and this is 3, right? So we can have group 1, group 2 and group 3. Okay, so we can take here C out equal to, what is group 1? This is AB plus, what is group 2? If you go here vertically, then A is constant and this way it is C, right? So this is C in, by the way, C in. And for group 3, if you go vertically, B is constant and this way it is C in. Okay, so it's simply AND gate. This and 3 input OR gate, we can say 3 input OR gate. Okay, this is the expression for C out. So for expression for sum, S is A plus circle B plus circle C in, and for carry out, this is the expression. Now if I want to draw this circuit for this AND gate, for this full adder, then I can consider this A, this is B and this is C. A, B, C. So this is A, B, C in. Okay. So for sum, this is A, B and C. It's an XOR gate. So this is sum S. And for carry out, it is A, B, both are ANDed. Then we have A, C, again both are ANDed. Okay, I just need to extend this line. And this is B, C in, again both are ANDed, and all these three are ORed with each other. This is a OR gate. Okay, this is carry C out. Okay, so this complete is the circuit for full adder. This is how full adder circuit is. And if you try to provide the different input combinations as we have seen for this truth table, then you should get the same values. Now just if you try for any of this input combination, so you should get sum 1 and carry 0 for this input combination if you are considering this circuit, right? So this is XOR gate, as I said, 3 input AND gate. So this is 3 input OR gate. This is OR gate 1, 2, 3. Okay. So I hope you understood how we have used the concepts of K-map to design the circuit of this full adder or half adder. So in the exam you may have a question, simple question. So question would be design a full adder circuit. That's it. Design a full adder circuit is the question. Okay, and this is the answer for that. So full adder, you have to go for this block diagram. This truth table is very important, right? And from this truth table, since we have 2 output columns, we have taken this K-map for sum, and from that we have derived this expression. Okay, and then we have gone for K-map for carry, and then we have derived this expression, and using both the expression we have drawn or we have designed this circuit, right? So that is what design. Okay, I hope you understood this. So in the next lecture we'll go for similar concepts, that is binary subtraction, right? Till then, have a nice time. Thank you.